Final presentation in Unit 7 entitled Can't the Machines Do It says the Industrial Revolution was another one of those extraordinary jumps forward in the story of civilization. So, the first thing we want to look at is we want to look at our learning goals. And the first one is that students will be able to relate the heat energy to mechanical energy. And they'll be able to describe the laws of thermodynamics on both a macroscopic and a microscopic scale. And that they'll be able to apply the laws of thermodynamics to heat engines. So, if we look, the first thing that we already know is that heat can be added with no change in temperature. We've already saw that right here with a change in phase. So energy can be added as far as changing phase, and energy can be converted from one type to another so long as it's conserved. Remember, that's a whole law of conservation of energy idea. You can take work and you can go to gravitational potential energy, or you can go to kinetic energy, or you can go to heat. You can go to lots of different things as long as that energy is conserved. So, what we learned in the lab is that heating a liquid can change the phase, and that you can funneling the steam into a small area can increase the push, or what we call the force. And the gas can be used to do physical work. So we actually took this thing and we used it to turn this pinwheel, and when it turned the pinwheel, it was actually doing physical work. Now, the key vocabulary for this particular section is that number one, the system. The system is whatever you're looking at. It's the collection of matter that's being studied. So, for example, if I'm looking at water in a beaker, the water in the beaker is my system. Okay. Now, everything that is, excuse me, not what I'm looking at is called the surroundings. So the beaker, the air around the beaker, the hot plate, the air in the room, all the rest of those things are the surroundings. Now, the good thing is you get to define the system as whatever you want it to be. So the surroundings is everything else. Now, thermodynamics, the definition of thermodynamics is the relationship or the study of the relationship between heat and work. So how can you take heat and turn it into work? How can you take work and turn it into heat? Now, one other thing that's going to come up a little bit is the idea of entropy. Now, entropy is the energy without the ability to do work. Generally, it's referred to as disorder in a system, but disorder is kind of a not a great term for it. What you can think of it as is it's irrecoverable energy is the way to look at it. Now, the zeroth law of thermodynamics. I know it's weird, they start at zero. But the zeroth law of thermodynamics is thermal equilibrium. If two systems are in thermal equilibrium with a third, then they will be in thermal equilibrium with one another. So, for example, this is 50 degrees Celsius and is equilibrium with this box. This is 50 degrees, and this is in thermal equilibrium with this box. What can you say about the first and the third boxes? Well, they have to be in thermal equilibrium with one another. And it doesn't matter what this is, it's going to be 50 because they're in thermal equilibrium with one another. So the zeroth law of thermodynamics just says if two things are in thermal equilibrium, then they have to be in thermal equilibrium with a third if one of them is. It's kind of a common sense law. The next one is the first law of thermodynamics. It says heat and work are forms of energy that cannot be created or destroyed, but can flow into and out of a system, and that should be very, very, very familiar. This right here is basically a restatement of the law of conservation of energy, which we talked about in Unit 5. It's the whole idea that you can take heat, you can take work, you can turn them into different things. In this case, it's saying you have a system. Here's my system. The system in this, or the energy in the system is constant unless you allow energy to go out of the system. Okay, that's the only way the energy can change, or if you put energy into the system. In other words, you can't create energy from nothing, you can't destroy energy, but you can let it into and out of the system. Now, this idea of the law of thermodynamics actually led to the idea of the steam engine. So we're taking heat and we're using the steam to actually propel something like a locomotive. An example of the first law of thermodynamics is the idea of taking heat and using it for mechanical energy. Now, this is how the vast majority of electricity is produced. So you have nuclear power, coal, oil, natural gas, all of these things right here are sources of heat. And what they do is they burn them, set them off, have a nuclear reaction underneath water. So here's your source of heat, here's water. What happens is that water turns to steam. As it turns to steam, the steam is used to turn these things right here. These things are what we call turbines. Whenever this turbine turns, okay, it's got magnets on it. And whatever, we'll talk about this later in the year, but as you turn magnets, it actually creates electricity. So the fact that you have heat, take water to steam, okay, it takes that steam, and then use that steam to do work in producing electricity. So it's the whole idea of taking heat and actually using physical work out of it. Now the other idea is you can actually use mechanical energy to produce heat. And you see this whenever you see a railroad car moving. It's got one of these things right here. Whenever you turn it, you can see sparks coming out of the side. It's going to be very, very, very hot. The energy, the kinetic energy that it has is very, very high. You can also see this if you've ever gone target practice shooting. If you take a bullet and you fire it into a wall and then you come back here and you try and touch the bullet, don't do that. The reason why you don't want to do that is because it's very, very, very hot. You have to give it time to cool down. That's the origin of the phrase hot lead. Okay. Next, we have the idea of this is the first law of thermodynamics put it into an equation form. And the equation form is delta U equals Q plus W. So Q, remember, is heat, and we're familiar with that from our previous presentations. W represents work, and we're familiar with that from Unit 5. What's new in this particular occasion is the idea of delta U. Delta U represents what we call the change in internal energy of a system. So it's the change in energy for a system. Now, remember we said heat can flow into or flow out of a system. So this can be a positive or a negative number depending on whether you're adding energy in or taking energy out. Now, one of the things that's pretty tricky about this equation is depending on your textbook and depending on just how they decided to write it, sometimes you'll see it as delta U equals Q plus W, sometimes you'll see it as delta U equals Q minus W. But really, it just depends on the system itself. So here's the way to think about it. Think about it as Q plus W. And then what you do is you say Q is going to be positive if heat is transferred into the system. So if I add heat, heat is positive. If I take away heat, heat is negative. Okay, so you see the difference in heat. Heat's pretty easy. It's work that's the tricky one. But think about it this way. If you take a balloon and you squeeze that balloon down, what you've done is you've added energy to the system. The reason why you've added energy to the system, if you were suddenly to remove your hands, that balloon would expand back out real quick. So what you've done is by pushing on the balloon, you've increased the elastic energy of the system. So you've added energy to the system by compressing it. So if you take a system and you compress it, if it gets smaller, we say that that is a positive work value. Now, if you take a system and you actually let it expand or you stretch it out, we say work is done by the system, so the system loses that energy. So if a system expands, work is negative. If a system compresses, work is positive. So let's take a look at a couple of examples with this. The first one says this is how an engine works. The piston of an engine expands 0.10 meters. How much force does this piston expand with if it occurs at 500 joules of heat is added to the system? So we have the whole idea of delta U equals Q plus W. Now we have a closed system, so it doesn't say anything about delta U or anything like that, so we're going to say that this is what's called an isothermal system. In other words, there is no change in energy to the system. So what that means is that the heat input, okay, is going to go into the expansion, I'm going to put expansion of the system. Okay, now remember, that meant that this value would be negative, so you actually have Q minus W equals 0. So when I move it to the other side, it's going to be Q equals W now. So we have this whole idea that it's expanded. Now I do know that there are 500 joules of heat added to the system. I do know that this right here is work. Remember, work from our previous units is force times distance. So this simplifies to this, or 500 equals F times 0.1. Whenever you solve at this point, you would say that F is equal to 5,000 newtons of force. So what you would say is this piston expands upward with 5,000 newtons of force. The next one says a balloon filled with gas is heated with 500 joules. What is the change in energy when the balloon expands with 200 joules of energy? So we hold the whole idea of we're trying to solve for delta U in here. We're trying to say what is the change in energy. So I do know that the Q value is a positive 500 joules. And the reason why I know it's positive is because the gas is heated. Heat is added to the system. I also know that the balloon expands with 200 joules of work. So remember, whenever you allow the system to expand, what you're doing is you're losing that potential energy that it has stored, so this becomes a negative value. So you would use the equation delta U equals Q plus W, and you would say 500 plus a minus 200, which gives you a value of 300 joules. Okay, this next one says a fire syringe. This is actually a cool little device right here. You can actually take this syringe and you can plunge it down, and because it's plunging and compressing the system so much, it creates a lot of heat and it actually increases the temperature quite a bit. Whenever it increases the temperature quite a bit, it can actually spark. So that's a really cool, interesting little thing. It's a way of being able to start a fire, and it doesn't require flint because flint will wear down. So it's a pretty nifty little device. So it says you have a fire syringe. It says there's 5,000 newtons of force is necessary to compress the cylinder 0.2 meters. You should recognize that's a force and it's a distance, so we'll be able to calculate work from those. Also, it's compressing the system. So whenever you're compressing the system, that means that you're adding that much energy to the system. Now it says the cylinder contains 2 grams of air, and it gives us a specific heat value, and it gives us an initial temperature, and it wants us to know what the final temperature of this particular air is going to be as a result of it being compressed. So the first thing we're going to do is we're going to say, okay, well, this is a system. So since this is a system, I'm going to say that there's no energy flowing into or out of the system. I'm going to say all of the energy is going into making this air change its temperature. In other words, I'm going to say delta U equals 0. Okay, so when I do that, I say delta U equals Q plus W. Okay, so I have Q, but I don't really have Q. What I'm trying to do is I'm trying to solve for the final temperature. So I'm going to have 0 equals Cm delta T, and then on the other side, I'm compressing the system, so I'm going to have the whole idea of my force times my distance. So force times distance. Okay, so what we can do is we can set these things equal to each other now. We're compressing the system. Whenever we do this, we can now say that you have 5,000 times 0.2 equals, on the other side, let's go ahead and erase, let's make some room. You have 5,000 times 0.2 equals C, which is our 1.0035, M, which is our 2 grams, and then our delta T. And our delta T is going to be our final temperature minus 23 degrees Celsius. Okay, so all you have to do at this point is divide both sides by this 1.0035 times 2. And then once you do that, you need to add 23 degrees to both sides. When you do that, you actually end up getting a very, very high temperature value. The change in temperature is 498, which actually when you add it to 23 puts it over 500 degrees. So we'll go ahead and round it off. We're going to say it's about 500 degrees because you are going to lose a little bit of heat to the surroundings. So it's going to be roughly 500 to 520 degrees is going to be the temperature of this thing just by pressing it down. Well, that right there is enough to actually take something like paper or a little bit of kindling and actually light it on fire just by compressing the air. So now we have a heat engine, and a heat engine is any device that transfers energy between heat and work. Examples of them are engines, like a steam engine or the engine in your car. Another is a refrigerator, an air conditioner, even what we call a bimetallic strip would be an example of transferring between heat and work and heat. So, for example, a bimetallic strip is just a strip of metal that consists of 2 metals, and whenever you heat one heats up faster than the other because they have different specific heats. As a result, this strip will curl. Whenever it curls, it's actually bending. There's a force being applied across a distance, so you've taken heat and converted it into work. An engine is where you use gasoline or some sort of heat to actually cause a piston to move, and whenever the piston moves, you do work which propels the car forward. A refrigerator actually does work on the gas in the refrigerator. It'll actually take the air and will expand the air out. Whenever it expands the air out, it actually decreases, it takes heat out of the system, so the temperature will drop. So refrigerators and air conditioners work much the same way. They have pumps that actually expand the air, they allow the air to expand, and allowing the air to expand, it cools. Geothermal energy is an interesting system that some people are using to create electricity. And what you do is you actually use the earth itself as a source of heat or steam. So you have what we call a production well and an injection well, and you hook up what we call a geothermal plant. So these two things right here, you actually pull up water from the earth, and you have sort of a flash tank. Now, the nice thing about a geothermal energy is it's always the same temperature. It depends on where you are, but it's about 68 to 72 degrees once you get, I think, 40 to 50 feet down. So the temperature is always the same. Well, you can actually use this to heat and cool your house, or what you can do is you can actually use this, you can pull this water up, run it through a turbine, cool it down, and pump it back into the earth, and you have this same continuous cycle where you're not using any water and you're not having anything that's being used. Okay, now another geothermal idea for heating and cooling is if you just take this water that's, it's hot outside, and you pump 68-degree water in, that water is going to absorb some of the heat in your house, because you wouldn't produce electricity in your house, but it's going to absorb some of the heat in your house, and then you can return it back down where it will go back to 68 degrees. So you have a continuous flow of cold water into your house, and that continuous flow of cold water into your house will take heat with it. Likewise, in the winter, when it's 20 degrees outside, you have 68-degree water that's coming up. It's taking some of that, it's giving some of its heat off, and then it's going cycling back down. So it's a way of geothermally heating and cooling your house with the same system. Now we have the second law of thermodynamics, and the second law of thermodynamics is just basically saying heat spontaneously flows from high temperature to low temperature, and that's something we've talked about with thermal equilibrium. But the second part of the law of thermodynamics is that reactions are never 100% efficient. Okay, there's about 100, I think there's like 180, it depends on your car, how big your car is, but some cars are capable of getting about 180 miles per gallon based on their size. But the problem with that is you will never ever get that from a car, not just the way they're designed now, but ever. And the reason is you can never take 100% of the energy and transfer it from something to something else. And I know a lot of you are saying, well, the law of conservation of energy, it has to. All the energy has to go somewhere. And that's true. But what happens is if I'm trying to convert heat to work, what happens is even in the best case, let's say I have 100 joules of heat, I can get 98 joules of work, and then 2 joules go to what we call entropy. And entropy is just heat energy that is unusable heat energy, is the best way to think of it. It's disorder of a system. So you're always going to lose some energy to entropy. And this is the second law of thermodynamics continued. It says the entropy of the universe always increases. Now, it doesn't always have to increase for a system. So for example, whenever you have a refrigerator, entropy actually goes down in a refrigerator. But entropy actually goes up outside the refrigerator. So for the net universe, entropy is always increased. Okay, you might have tried this. If you've ever had a hot day, if you can seal off your kitchen and you were to open up the refrigerator, it would actually get hotter. And the reason why is the pumps on the back of your refrigerator actually produce more heat than they actually cool. It's the whole idea of some of it's always lost to entropy. So as temperature increases, entropy increases. So as you increase the temperature, more disorder, more movement, more entropy. Also, as the phase change goes towards gas, entropy increases. So Proficient 1 says which phase change will increase the energy of water in the water cycle. Say the entropy of water. Okay, so as it increases the entropy of water, it's the evaporation is the first obvious one because that's the one that goes to gas, and also whenever you melt. Those are the two ones that actually increase the entropy of a particular cycle. Next, it says the air conditioning breaks on a hot day, so a student steals off the kitchen and opens the door. Describe the temperature and entropy in this room. We already talked about this. The temperature will actually increase, and then the entropy will also increase because these two things go together. Now, the reason why the temperature increases is because on the back, there's an engine that's actually using energy to pump out hot air. But it takes more energy to create this heat and pull this out and make cold air than you actually get out of it. So it may require 100 joules of heat to lose 80 joules of heat here. Now, where did the other energy go? The other energy went to entropy and just went to heat. So it is never 100% efficient reaction. Well, if you were to look at this, you have a net gain of heat. So because you have a net gain of heat, this won't work. Now, if you stand directly in front of the refrigerator, it will feel cooler, but the overall temperature of the room will actually increase. And finally, expanding the first law of thermodynamics. This is more of an extension, but you can actually take this thing and you can simplify it by expanding it out. So whenever you have an adiabatic system means that there's no change in heat. What that means is this becomes zero. When this becomes zero, under an adiabatic terms, this is delta U is equal to P delta V. Now, P delta V is more of a common term whenever we're looking at this law of thermodynamics. It is the same thing as work equals force times distance. Force times distance and pressure times change in volume are the same thing. Now, an isothermal system, we can't say that Q is zero anymore. Instead, when we have an isothermal system, we say that this is zero. Whenever we do that, what we can say is that Q is equal to minus P delta V. Okay, so all the heat that's going to go into a system will actually go into expanding that particular system. The next one we have is isochoric. Isochoric means that there's a constant volume. Well, if there's a constant volume, then the change in volume is zero. If the change in volume is zero, zero times the pressure is zero. So what we get is the change in energy of the system is equal to the heat added to the system. And finally, we have an isobaric system, and an isobaric system has no change. Okay, notice how this is not change in pressure, it's just pressure. So because of that, there's no simplification for an isobaric system. So if we were to look at an adiabatic system where no heat is transferred, that's what we tried to do with the styrofoam cups. We had one styrofoam cup, and then we wrapped it with another styrofoam cup to try and make it so that there is no heat loss. Okay. That's what we were trying to do with our one experiment in 7.2. An isothermal system is one where that it changes at there's a constant temperature. It's really hard to do, but there are some isothermal devices that you can use. An isochoric system is any time that you have something that's capped. So, for example, let's say that you're doing an experiment in a beaker, and you cap that beaker. Well, once you cap that beaker, this right here is a constant volume, so it's an isochoric system. And then an isobaric system is any one that's open to the atmosphere. So if you're doing something in an open beaker, the atmospheric pressure is 1 atmosphere and it's constant throughout.